So I will speak about weakly and semi-supervised machine learning methods. So settings. As usual, we have data set. You can think as a table. We have features, x1, and so on, xn. Then we have sample size n, and you can think about patients in clinic. So every patient has temperature, blood pressure, and so on. And we have, for every patient, we have label sick or not sick, or which exactly disease he may or she may have. And this is exactly why. So we call it target feature labels. So if y is known, we speak about fully supervised learning. If y is partially known, we speak about semi or weakly supervised learning. And if y is unknown, we speak about unsupervised learning. So goal is to find decision function f, which predict y values for any new patient which come to the clinic. So we train function f on existing data set, and then we use this function to predict new values. This should be very well-known settings, nothing new here. So just motivate ourselves. This plan of this talk. So we introduce semi and weakly supervised regression problem. It could be also used to classification problem. There is no big difference. So we propose a method which combines manifold assumption, graph Laplacian, and cluster ensemble. It's also called collective decision-making methodologies. Then we solve an auxiliary minimization problem. So practically we get function f, decision function f, and then we demonstrate some numerical results. So all ML machine learning problems can be classified as fully supervised, semi-supervised, weakly supervised, and unsupervised. So fully, it's when, as I said, target label is provided. Semi-supervised learning, only a small portion of the data is labeled, while the majority remains unlabeled. So goal is to use both the labeled and unlabeled data to improve learning accuracy. So we ask practically ourselves, can we use unlabeled data to improve learning accuracy? So assumption is that data build some manifold, have some special geometry, and we can use the structure in data to improve quality. So weakly supervised are problems where target labels are incomplete, inaccurate, noisy. Medical images have very often think about RMI or CT images. Sometimes it's not clear if this part of human organ is damaged or not, or think about satellite pictures. The satellite pictures provide photos of pedestrians, and sometimes you do not know if it's pedestrian or shadow of a tree, for example. Okay, other examples where we can see this type of problems is spam detection in emails. Some users report that this is a spam. Some spam is actually not spam, it's real conference. Fake news detection, fake review detection, medical image classification, sentiment analysis in media. For example, very hard to identify sarcasm. Oh, great, another flat tire. Oh, great, another good talk. User behavior analysis in recommendation systems. Brief introduction is here. Much broader list of motivating examples include autonomous driving, speech recognition, text translations. For example, some words, some sentences can be translated in different way, and all of them could be correct or partially correct. Bioinformatics, drug discovery, protein structure, prediction. So just repeat again, fully supervised learning assumes we are given a set of target labels. So domain definition for each target label. So Y is provided by a certain teacher. Goal is to find a decision function f for predicting target feature value y for any new feature vector x from the same statistical population. The decision function should be optimal in some sense, for example, minimize loss function. So methods also very well known. There are many methods: regression, neural networks, k-nearest neighbors, decision trees, decision forest, support vector machine, and so on. Unsupervised learning. So you have set of users, set of movies, and you let your algorithm run and hope that this algorithm classify your set of objects in certain clusters. And so we introduce here partition P. Partition consists of K clusters. So if we do in other settings, we may have less or more clusters here and different clusters. So obtained cluster partition can be uncertain due to a lack of knowledge about data structure. Parameters of the learning algorithm it could depend on random initializations. So method to solve unsupervised machine learning problems are clustering, for example, k-means and all kind of modification, dimensionality reduction, anomaly detection, generative adversarial networks, and all these methods are, especially clustering, k-means, very well studied. There are many modification. Drawbacks of these methods also well known, and remedies also already developed. Oops. Here, so one of particular cases. So if assume that we have two data sets, blue and red one, and we run different clustering algorithm, this unsupervised learning, and three methods can provide this partitioning, like first one, third one, and number four. And one method built a hyperplane here, and everything what is below identify as a blue class, and everything what is above red class. Yeah, in these settings we can run consensus algorithm, and consensus partitioning will be like this because three methods decided that this partitioning is a correct one. Oops. Yes. So please remember this abbreviation, semi-supervised learning, CCL. The target feature labels are known only for a part of the data set. We will define this data set X1. Usually it's 5 or 10 or 15% of data. So we have N1 data which are labeled, and the rest we defined it's X0 unlabeled. So totally we have N samples, N1 as have target variable labeled, and the rest is unlabeled. So our goal is predict target features either for given unlabeled data from X0 or for arbitrary new observations from the same statistical population. Yeah, as I already mentioned, to improve prediction accuracy of F, both labeled and unlabeled datasets are used. Practically in this work, we check our hypothesis that unlabeled data and uncertain data can be used to improve quality of forecasting. Of course, it's problem dependent, and of course, it depends how many uncertainties we have. And later we will see it in numerics. Weakly supervised learning. Also, please remember this abbreviation. Weakly supervised, it's very similar to semi-supervised, but we add assumptions that some data are uncertain. Let's say we are not sure if it's pedestrian or shadow of a tree. So we can say that it's 70% pedestrian and 30% is shadow. Of course, one approach is to do pre-processing and clean the data and use only very reliable data. There are debates in scientific literature about this, and I will provide reference. Me and my colleagues belongs to the scientists, to the group, which thinks that to use uncertain data, it's beneficial. Okay, another motivating example. This is paper of my colleagues who are also co-author of other our joint papers. So we have CT image of a brain slice. So it's needed to forecast stroke, I think, stroke area. So this original image, this is exact, accurate area where there are some damages, and very inaccurate mask or annotation is this one. This could be done automatically by some software or by unexperienced staff, medical staff. Okay, now we come to mathematical modeling of which we use in weakly supervised learning. To model uncertainty in the label identification, we suppose that for each is point, I remind N1 it's a label dataset, the value y I is a realization of random variable, this one capital Y, with a distribution function fi defined on some dataset dy. As is very usual, we assume that this distribution belongs to a given distribution family. So further, we assume that this random variable, target random variable, is a Gaussian, and luckily Gaussian can be parameterized by just two parameters, mean value and standard deviation. So we assume that mean value is equal target and standard deviation is equal SI. They are known for each labeled observation. So I remind we have this 10% labeled data N1. And for strictly determined observation Y, we postulate a normal uncertainty model with, so practically we say that standard deviation, if we know exactly label, then standard deviation is 0. So that's both labeled and so uncertain and certain data fit in this model. So we aim at finding a weak labeling of points from unlabeled sample. So x0, it's this 90% which were unlabeled. With other words, we try to identify cumulative distribution function fy for I changing from this interval. Okay. So semi and weakly supervised learning settings require some assumptions, and we use two assumptions here. Cluster assumption tells us that points from the same cluster often have the same labels or labels close to each other. it could be also considered as a smooth assumption. Practically, if you have 2 points which are close to each other, then values of function in these points should be also close to each other. We do not allow jumps or discontinuity. Second is manifold assumption. Data luckily lives on a low dimensional manifold within the future space. So very often, even though we have high dimensional data, in reality, data belongs to some low rank manifold. It could be very hard to find this low rank manifold, but sometimes it's there. So if data are random, could be that there is no low rank manifold, but often there is this low rank manifold. So reference here from Belkin manifold regularization. Okay. So optimization problem. So let us, we have set of cumulative distribution functions for the whole sample set, labeled and unlabeled. And as I said, every single CDF is parameterized with 2 parameters. So we are trying to minimize this functional. So we are going over all possible CDF functions so that this sum is minimized. The first term in the sum is over labeled data where we know target variable. We know that these patients are sick. And this over all sample set, both labeled and unlabeled. So we have here may be useful to think about data as about graph. So vertices, in the vertices of graph, we have our data, let's say movies of patients, or people in social networks, and edges are connection. So if I know somebody very well, there is a strong connection, strong weight between me and this person. If 2 movies belongs to the same genre, again, strong connection. So here, decalligraphic, a statistical distance between 2 distributions. Here we may use Wasserstein, Kolmik-Liebner divergence, and some others. And W is similarity matrix. And gamma is just a constant. So first term, we reduces, when we minimize it, first term is responsible for reducing dissimilarity on labeled data. So x1 is labeled data. And second term is a smoothing. So if 2 points are close to, if 2 movies, 2 patients are similar, demonstrate the same features, then connection is strong, and to keep this term let me say like this. If 2 patients are very similar, then they are strongly connected. And it means that this distance should be very small because they're similar. Yeah, they're not very much different. Yeah. Okay, I hope it is clear. So we use Wasserstein distance. Definition is VP. So it's complicated formula for 2 statistical distributions. And luckily, there is nice formula, particular case if both distributions are Gaussian. So in this case, if P is Gaussian, Q is Gaussian, then this Wasserstein distance transformed in this sum. And intuitively, we can think about Wasserstein distance as about Earth mover distance, which measures how much work is needed to transform one probability distribution into another. It tells you the minimal effort, amount of sand moved times distance moved required to reshape one pile into the other. Okay, because very specific case, we can build analytical formula for our functional, which we are going to minimize. So this complicated functional, which was written here in 2, now transformed into this. We also added here L2 regularizer. It's increased stability and prevent overfitting. This one. So, and it's actually very important, right, to find the right choice for this weighting matrix. There are many possibilities how to take it. For example, you can take something like covariance matrix, exponential or Gaussian covariance matrix, which actually tell you that if points are close to each other, then weight is also higher. So it's describe how different points connected. But we do not do it. We take similarity matrix, and later I will show how we construct similarity matrix here. Okay. So now, because it's quadratic polynomial, and unknown here are these weights, these parameters, mean value and standard deviation, and we want to minimize this functional. We know all how to do it. We simply compute partial derivatives with respect of these parameters, mean values, standard deviations. We obtain large linear system. We solve this large linear system, and solution will be optimal parameters which minimize this functional. And yeah, because of our choice, we have analytic expression for this. We even do not need to do it approximated. It's simply analytical closed form. So if we compute derivatives with respect of mean values, we receive this one, number 4. We can simplify it, and it will be like this. Okay. So difference is that here I is changing from 1 to n to the over all samples, and here in 5 over unlabeled data. Okay, then we introduce graph Laplacian, where there is diagonal matrix and elements are computed as a sum. We speak later about this matrix. So here, short remark about also normalized graph Laplacian. Normalized Laplacian is computed as this by this formula, where D is degree matrix. It's a diagonal matrix, tells how many neighbors each node has. Yeah, the connections every human has in social media, for example. And W is adjacency matrix. Actually, it consists of 0 and 1. So if two objects, patients, clients are connected, it's a 1. If not connected, then 0. So graph Laplacian regularization is used in machine learning to enforce smoothness of a function defined over the nodes of a graph. It minimizes variation of the function over the graph, encouraging similar values for neighboring nodes connected by edges. In weakly or semi-supervised learning, the graph Laplacian is used to enforce smoothness in learning tasks where only a small amount of labels data is available. So just remember, in vertices of graph, we have our data, and we have not many data, and we use graph Laplacian for smoothness. It's actually, if 2 points are similar, then the labels should be similar too. Okay, this was short remark. This is another example. If you remember, this was a part of this functional G, which we minimize. And this is example of a graph and graph Laplacian, how it's look like. Okay. Yeah, a few words about spectral clustering. Sometimes when we run clustering algorithm in unsupervised learning and clustering algorithm, we need to estimate this matrix. Yeah. And that's why we need accurate clustering algorithm to get better estimation for this matrix. Yeah. And so here's one of useful features of spectral clustering. And what is spectral clustering? So practically if you look on the picture, we have a very famous example. It's called two moons example. So k-means, it's very famous algorithm, fails to predict this two non-convex dataset. So actually this should be one cluster, this should be another cluster, and k-means build hyperplane here. Everything what is right identify as a yellow class, everything what is left as a dark class. But if we compute graph Laplacian, compute eigenvalues, so smallest eigenvalue is always zero. It's a property of graph Laplacian. And if we take first non-zero eigenvalue and corresponding eigenvector, then we can transfer this data into another space. And in this space, clustering is much easier. So this is, for example, visualization of eigenvector which corresponds to the first non-zero eigenvalue. And if we run k-min on this data set, then we get perfect, correct clustering. So this slide illustrates useful properties of k-Laplacian. Okay, coming back to our equation, we introduce some vector. Practically, this is our target labels, well known. This is unknown target labels. We built matrix B. So B was a learning factor, or just a scalar factor in functional G, which we minimize. We build this diagonal matrix. It's such auxiliary matrix and vectors. Point is that now our minimization problem is transferred, 4 and 5 is transferred in this one, and here we have already graph Laplacian. And B is diagonal matrix, and this is vector right-hand side, which is defined here. And I remind that if we solve this linear system, we receive our parameters which we need, yes? And this is exactly solution. So this is bottleneck of the whole computational process. We need inverse of this densely populated matrix. And the same for standard deviation. So only right-hand side is different. So practically our minimization problem now was transferred to solution of these two linear systems. Actually, yeah, these two. If we solve them, we define these parameters, we defined cumulative distribution functions, which minimize our functional. Okay, another useful, because it was bottleneck, it was hard to work with large data set. Trick which we did here, we approximated this densely populated matrix with truncated single decomposition with adaptive cross approximation. So, and we used well-known Woodbury formula, which tell you if you have some dense matrix and you have inverse, you already computed, invested some time, and then you have low rank update of this matrix. Can you say something about inverse of this? Can you compute inverse of the new matrix in a cheaper way? And this is also a very well-known result, very old one. And result is positive. This is 10 is classical linear algebra theory. So this update could be computed much cheaper. This is point. And we apply this trick. This is a little bit complicated formulas, but this is exactly this Woodbury formula here. Okay. And we were able to reduce complexity from cubic to quadratic. Okay. You remember I told you that it's very important to find right choice for matrix, for this matrix, weighting matrix. And what we are doing in this work, we do not take covariance matrix, we take co-association matrix. So how it is built? Assume we have 6 data points. This is our sample. And we run one clustering algorithm. And one clustering algorithm give us 3 clusters, C1, C2, C3. And this is partitioning 1. That's why we have in the top index 1. Then we change slightly initial settings. It could be, because they're uncertain or we do not know. And another clustering algorithm give us another clustering. Now objects 1 and 3 belongs to one cluster and all other to another. We run third clustering algorithm and again get another partitioning. Now we can build matrix V, which tell us how often a pair belongs to the same cluster. For example, 1 and 2, it's a first row, second column. 1 and 2 belongs to one cluster one time, and here also in this partitioning. So it's why we have number 2. Number 5, so 5 and 6, it's exactly this element 2. 5 and 6. Here to different clusters, here to one cluster, and here again to one cluster. So number 2 here. And so on. If we do it for whole data, we get such matrix. And in numeric, we will show that it's better to use such matrix as a covariance, for example. So we come to numerical section. So I introduce abbreviation, weakly supervised regression algorithm based on low rank representation of the co-association matrix. It's why it's this long name. So it's exactly algorithm which we introduce and we run it. And we show that it's better than some equivalents also, which are not bad actually. So this algorithm actually summarizes what I told. We have X data set. We have these parameters, mean value, standard deviation, 10% of data. So we know these parameters for 10% of data. Yeah, then we have, to get better stable results, we run it R times, this mean clustering algorithm. Omega is all other parameters, and output is exactly these two vectors of length. With help of these two parameters, two vectors, they contain parameters, we can predict target variable for unlabeled data. Okay. So we generate R variants of clustering partitioning for parameters randomly chosen from parameter set. We calculate one co-association matrix V. Then we can build graph Laplacian. We can put all these matrices into our formulas, and we can compute all mean values and standard deviation, which parameterize our CDF functions. Okay, first example, we have a mixture of two multidimensional normal distributions, mean values from the space. We define ground truth, 1 plus noise, 2 plus noise. Noise is Gaussian also. So we use Monte Carlo modeling, where we repeatedly generate samples of size n according to the given distribution mixture. So we have this milk. Then we introduce 66% for train, 33 for test. In the train data set, we say that 10% are fully labeled, 20 inaccurately labeled, and the rest 70% unlabeled. We also introduce inaccurate, so random inaccurateness in our labels. So intuitively, we all understand that if we use, it's beneficial to use uncertain data only if uncertainty is kind of limited. And this parameter sigma is responsible for this level of uncertainty. If uncertainty is very high, then it's better to remove this uncertain data and do not use them at all. And this is later in table, you will see that if this parameter uncertainty level is growing, then our weakly supervised settings algorithm converge to semi-supervised. It means that it's equivalent when we simply deleted all uncertain data where uncertainty is very high. Okay. So it's in some further settings. We ran some tests and we identified numerically that good, more or less good scalar values which are used in functional G, which we minimize. So we use mean Wasserstein distance, which is defined like this. So it's differences between what we computed and ground truth. And we compute this. So our algorithm, let's say in jargon, with algorithm which is based on radial basis function, which just looks like a Gaussian covariance matrix actually. And so we run repeat 40 times. And this is stable data set, noise level, and this is our algorithm. This is algorithm, also good algorithm, but without low rank and without poor association matrix. And due to fact that we use low rank approximation, we can tackle problems of size 10,000 or even 100,000 or 1 million. This we cannot. Matrices are too expensive. And when you compare error, actually error are comparable, yeah, but computation time is much much lower. Okay, another test we run, we compare weakly supervised with semi-supervised. So you can see it as you delete uncertain data. Yes, when you delete, you have semi-supervised. When you take into account your uncertain data, you have weakly supervised. And if level of uncertainty is low, then it makes sense to use uncertain data. So we profit from geometry of data, from structure of data, from clustering structure, and this is error. So this error for weakly supervised 4 times smaller than for semi-supervised. If level of randomness is increasing, then this error also starts to increase. And if it's high, 0.5, then we see that these two errors becoming close and close to each other. It's exactly what we intuitively expect, yeah? When data are very uncertain, then it will be less and less profitable to use them for construction of beta classifier. Okay, second, last example, I think. So it's a gas turbine where for CO and NOx emission data set. So everybody can download it here. There are so many, N is so big, dimension of features is 11. So time collected in this time interval. Actually, in data set, we can predict two output variables, carbon monoxide and nitric oxide. For our numerics, we predicted only carbon dioxide. carbon monoxide, sorry, carbon monoxide, 66% for learning, test 33. We assume that accurately labeled is just 1%, inaccurately 10%, other are unlabeled. So because data new, we run just more than 100 clusters. So we use this clustering to build similarity of this weighting matrix W. So our algorithm gave us this error and semi-supervised this error. So practically this results show that on this example, it makes sense to use uncertain data. Yeah, and this is this here we compare error with some other known algorithm like random forest with 300 decision trees, which is also very good and accurate and very popular with linear regression. And so error is smaller, but time is higher. Reason is for higher time because we repeat. Actually, one cluster would be enough, but if we repeat 100 times this clustering algorithm, we simply improve accuracy, so time is higher. So I come to conclusion. So in this talk, we introduced semi and weakly supervised regression problem. We formulated the loss function and we solved this minimization problem. We did strong assumptions that we assume that this target labels have Gaussian distribution. With this trick, we simplified distance and loss function so that we could analytically solve this minimization problem. We use, to speed up everything, we use different tricks like graph Laplacian, low rank techniques, co-association matrix. And with these tricks, we achieve either faster or more accurate results. But I would not generalize it. We are only for these assumptions and for this type of problems. Yeah, I think I can finish here. Thank you for your attention.
Thank you very much, Alex.